Chapter 1 Physical Quantities and Units. SI Units. Base quantities. All quantities in science consist of a numerical magnitude and a unit. SI units are based on the units of 7 SI base quantities, of which you need to be familiar with 5. Mass, kilogram; length, meter; time, second; temperature, Kelvin; electric current, ampere. Although it is not formally an SI unit, the degree Celsius is often used as a measure of temperature. Each of these units has a precise definition. You do not need to remember the details of these definitions. SI units, Système International des Units, are carefully defined units that are used throughout the scientific world for measuring all quantities. Base quantities are fundamental quantities whose units are used to derive all other units. Derived units. The units of all other quantities are derived from the base units. For example, speed is found by dividing the distance traveled by the time taken. Therefore, the unit of speed is meters divided by seconds. At O level or IGCSE, you will probably have written it as meter/second. Now that you are taking your studies a stage further, you should write it as meter per second. Key terms. Base units are the units of the base quantities. Derived units are a combination of base units. The unit of force is Newton. What is in base SI units? Units of Newton is equal to kg meter per second squared. Study tip. To break watts down to base units, use the format joule per second, then substitute in joule, and continue using positive and negative indices. Now, test yourself. Question number 1. The quantity power is a derived quantity and its unit, the watt, is a derived unit. Express watts in base units. Question number 2. Which of the following are base quantities? Time, speed, volume, energy. Question number 3. Which of the following are base units? Kilogram, meter squared, joule, Kelvin. Homogeneity of equations. If you are not sure whether an equation is correct, you can use the unit of the different quantities to check it. The units on both sides of the equation must be the same. Study tip. Try to work through the worked examples before reading the answer, and then compare your answer with the one supplied. Worked example. When an object falls in a vacuum, all its gravitational potential energy is converted into kinetic energy. By comparing units, show that the equation mg delta h is equal to half mv squared is a possible solution to this problem. Answer. Write down the units of the equations on each side of the equation. Left-hand side, unit of m, kg, unit of g, meter per second squared, unit of h equals m. Right-hand side, unit of half equals none, unit of m equals kg, unit of v equals meter per second equals kg meter squared second minus squared. Units of half mv squared equals kg meter per second squared equals kg meter squared second per second squared. Both sides of the equation are identical. Now test yourself. Question number 4. The pressure exerted beneath the surface of a liquid is given by the equation del P equals rho G del H, where pressure is P, H is depth below the surface, rho is density of the liquid, and G is the acceleration due to gravity. Show that the equation is homogeneous. Question number 5. When a sphere falls through a liquid where there is a drag force on it, Stokes' law states that the drag force F is given by the formula F is equal to 6 pi nRV, where F is the force N, Newton, N is the viscosity of the liquid, kg, meter minus 1, second minus 1, R is the radius of the sphere in meter, and V is the relative velocity between the fluid and the sphere. show that the units in this formula are homogeneous. Using standard form. One way to deal with very large or very small quantities is to use standard form. Here, the numerical part of the quantity is written as a single digit followed by a decimal point, and as many after the decimal point are justified. This is then multiplied by 10 to the required power. Study tip: mistakes are often made when dividing by the numbers in standard form. If you are dividing by the quantity, like 1.6 times 10 to the power negative 19, remember that 1 by 10 to the power negative x equals 10 to the power positive x. Correct example: A. The output from a power station is 5600,000,000,000 watt. Expressed is in watts using the standard form. B. The charge on an electron is 0.0000000000000000000000016. Express this in standard form. Answer: A. 5 times 6 to the power 9 watt. B. 1.6 times 10 to the power minus 19 coulomb. An added advantage of using standard form is that it indicates the degree of precision to which a quantity is measured. This will be looked more in detail in AS level experimental skills and investigations on page number 101 to 108. Multiples and submultiples of base units. Sometimes the SI base unit is either too large or too small. Prefixes are used to alter the size of the unit. Table 1.1 shows the prefixes that you need to know. Table 1.1. Prefix symbol meaning: pico p 10 to the power negative 12, anno n 10 to the power negative 9, micro mu 10 to the power negative 6, milli m 10 to the power negative 3, centi c 10 to the power negative 2, deci d 10 to the power negative 1, kilo k 10 to the power 3, mega m 10 to the power 6, giga g 10 to the power 9, tera t 10 to the power 12. These are the recognized SI prefixes. The deci d prefix is often used in measuring volume. Decimeter cubed is particularly used. Study tip: remember that 1 decimeter cube is equal to 1 by 1000, not 1 by 10 of 1 meter cube. It is really decimeter cube, hence it is 1 by 10 meter times 1 by 10 meter times 1 by 10 meter. Now test yourself. 6. The distance from the Earth to the Sun is 150 gigameters. Express the distance in meters using standard form. 7. The wavelength of ultraviolet light is 4 times 10 to the power 7 meters. Express this wavelength in nanometers. 8. Calculate the number of micrograms in a kilogram. Give your answer in standard form. Making estimates of physical quantities. There are a number of physical quantities where you should be aware of the rough values. For example, the speed of sound in air equals 300 meters per second. List of such values are given in appropriate parts of the study and revision guide. An example is Table 7.2 on page 62. Errors and uncertainties. Errors. An error is a mistake in a reading caused by either faulty apparatus or poor experimental techniques. Errors and repeated readings are discussed in more detail on page 106. Accuracy, precision, and uncertainty. Accuracy and precision are terms that often cause confusion. Consider a rod of true diameter 52.8012 millimeters. Suppose that you use a ruler and measure it to be 53 millimeters. This is accurate, but it is not very precise. If your friend uses a micrometer screw gauge and measures it as 52.81 millimeters, it is more precise. even though the final answer is not totally accurate. No measurement can be made to be absolute precision. There is always some uncertainty. If a result is recorded as 84.5 seconds, this implies that there is an uncertainty of at least 0.1 seconds, perhaps more. You might see such a reading written as 84.5 plus minus 0.2 seconds. The 0.2 seconds in this reading is called the absolute uncertainty. It is often convenient to express an uncertainty as a percentage of the reading. This is known as percentage uncertainty. Percentage uncertainty equals absolute uncertainty by reading times 100. Key terms. Accuracy is how close to the real value a measurement is. Precision is the part of the accuracy that the experimenter controls by the choice of measuring instrument and the skill with which it is used. It is refers to how close a set of readings measured values are close to each other. Uncertainty is the range of values in which a measurement can fall. Worked example, a technician records the length of a rod as 84.5 plus minus 0.2 meters. Determine the percentage uncertainty in this measurement. 0.2 divided by 84.5 times 100 is 0.24%. Precision of measurement. When making a static measurement, for example, the length of a pendulum, you should normally measure to the nearest division on the instrument. If the divisions are 1 mm or more far apart, you need to judge the nearest half division or better. When making a dynamic measurement, for example, the height to which a ball bounces, then the other considerations come into play. The ball is moving, so you have to judge when it is at its maximum height. This is much more difficult task. You can probably only measure this to the nearest 5 millimeters. Many digital stopwatches measure to 1 of a 100 second. However, the uncertainties in these reaction times of manually starting and stopping a stopwatch are much greater than this. The best you can manage is to measure to the nearest 1/10 of a second. Until 1977, world records of running events were given to a precision of 0.1 seconds. It was only the advent of electronic timing that it has become possible to record phase times to 1 of 100 of a second. The current world record for men's is 100 meters is 9.58 seconds. This suggests an absolute uncertainty of plus minus 0.01 seconds and a percentage uncertainty of approximately 0.1%. The knock-on effect is that for a world record to be valid, the track length also must be measured to a precision of 0.1% or better. This is an absolute uncertainty of 10 centimeters. Repeat readings. Precision can also be estimated from taking repeat readings. For example, when 5 readings are taken of time for a ball to run down a track, it is acceptable to give the uncertainty as half the range of the readings. Worked example, the time of flight for a projectile is measured by 5 technicians. The readings are 5.2 seconds, 5.2 seconds, 5.4 seconds, 5.0 seconds, and 5.1 second. Calculate the absolute uncertainty in these readings. Answer. The range is the difference between the largest and the smallest values. 5.4 minus 5 is equal to 0.4 seconds. The absolute uncertainty is plus minus 0.4 seconds by half equals plus minus 0.2 seconds. Now test yourself. Number 9. What is the realistic absolute uncertainty of a time measured using a handheld stopwatch? Number 10. A cylinder is machined to a diameter of 40.24 millimeters. Four apprentices are asked to measure the diameter of the cylinder using different instruments. The results are shown in Table 1.2, which apprentice gives the most precise result, the most accurate result. Combining uncertainties to find the uncertainty of a combination of variables, the rules are as follows. For quantities that are added or subtracted, the absolute uncertainties are added. For quantities that are multiplied or divided, the percentage or fractional uncertainties are added. For quantity that is raised to the power to calculate the final uncertainty, the percentage uncertainty is multiplied by their power and the result is treated as a positive uncertainty. Worked example. The currents coming into the junction are I1 and I2. The currents coming out of the junction is I. In an experiment, the values of I1 and I2 are measured 2.0 plus minus 0.1 A and 1.5 plus minus 0.2 A respectively. Write down the value of I with its uncertainty. Answer. I equals I1 plus I2, which is equal to 2.0 plus minus 0.1 plus 1.5 plus minus 0.2. The quantities are being added. So to find the uncertainties of the original quantities are added. Hence, I equals to 3.5 plus minus 0.3 ampere. Worked example. The acceleration of free fall g is determined by measuring the period of oscillation t of a simple pendulum of length L. The relationship between gt and L are given by the formula g equals to 4 pi squared times L by t squared. In an experiment, L was measured as 0.55 plus minus 0.2 meters and at t as 1.50 plus 0.02 seconds. Find the value of g and its uncertainty. Answer. G equals 4 pi squared times L by t squared equals 4 pi squared 0.05 by 1.50 squared equals 9.7 meter per second squared. To find the uncertainties, the second, the third rules are applied. Percentage uncertainty of L, T, and T squared are 3.6%, 1.3%, 2.6%. Percentage uncertainty in G equals percentage uncertainty in L plus percentage uncertainty in T squared. 3.6 plus 2.6 equals 6.2%. Absolute uncertainty in G equals 9.7 times 6.2 by 100 equals 0.6. Thus, G is equal to 9.7 plus minus 0.6 meter per second squared. It is worth noting that in this example, the question is asking for the absolute uncertainty and not percentage uncertainty. If you take the shortcut and leave your answer as 9.7 plus minus 6.2%, you will lose credit. Practical skill. It is also worth noting that it is poor experimental practice to take only one reading and try to find a value of G from that. You should take a series of readings of T and different reading lengths for L, and then plot a graph of T squared against L. The gradient of this graph would be equal to 4 pi squared by g. For further information about graphs, see rules for plotting graphs on page 103 to 104. Scalars and vectors. Scalar quantities and vector quantities. A scalar quantity has a magnitude only, example mass, volume, and energy. A vector quantity has magnitude and direction. Examples are force, velocity, and acceleration. Adding scalars. Consider two masses of 2.4 and 5.2 kg. The mass is 7.6 kg. The total is simply the arithmetic total. The adding vectors. When vectors are added in their directions must be taken into account. Two forces of n Newton and 5 Newton are acting in the same direction would have a total force of 8 Newtons. If two forces of 3 Newton and 5 Newton act in opposite direction, the total force is 5 minus 3 is 2 Newton in the direction of the 5 Newton force. If the two forces act at any other angle to each other, a vector diagram known as the vector triangle is used. See page 14. If there are more than two vectors, these can be added in a similar manner using a polygon rather than a triangle, provided that all vectors are coplanar, which means they are all lie in the same plane. Key terms. A set of vectors are said to be coplanar if all the vectors in a set lie in the same plane. Constructing a vector diagram. In a vector diagram, each vector is represented by a line. The magnitude of the vector is represented by the length of the line and its direction is represented by the direction of the line. If two vectors at a point, their resultant can be found by drawing a vector triangle. The following rules will help you to draw a vector triangle. Figure 1.1. Choose a suitable scale. Draw a line to represent the first vector v1 in both magnitude and direction. Draw a second line starting from the tip of the first line to represent the second vector v2 in both magnitude and direction. Draw a line from the beginning of the first vector to the end of the second vector to complete a triangle. The resultant vector is represented by the length of this line and its direction. Study tip. The larger the scale you choose, the greater the precision you should achieve in your answer. It is good to practice. Include your scale in the diagram. When measuring distances, use a ruler, and when measuring angles, use a protractor. Worked example. A light aircraft is flying due north with a velocity relative to the air of 20 kilometers per hour. A wind from 30° north of west starts to blow at 80 kilometers per hour, shown in figure 1.2. Calculate the velocity of the aircraft relative to the ground. Answer. Draw a vector diagram to a scale of 1 cm to 40 kilometers per hour, shown in figure 1.3. Length of the resultant is 1.35 centimeters. Multiplied by the scaling. Velocity is equal to 4.35 times 40 kilometers per hour equals 174 kilometers per hour. Measure the angle theta using a protractor. Theta equals 23 degrees, so the direction is 23 degrees east of north. You will observe that the directions of the original two vectors go round the triangle in the same direction. In this example, clockwise. The direction of the resultant goes in the opposite direction, anti-clockwise. Study tip. Compare the layout of your answer, figure 1.3. Is your layout clear? Can the examiner see what you have tried to do? This is important in calculations where some credit will be given even if an arithmetic error leads you to giving the wrong answer. Components at right angles, resolving vectors. Just as it is useful to be able to combine vectors, it is also useful to be able to resolve vectors into components at right angles to each other. Figure 1.4 shows a vector, v, acting at an angle, theta, to the horizontal. The vector triangle in figure 1.4a shows that this vector can be considered to be made up from a vertical component and a horizontal component. It is sometimes easier to use a diagram similar to figure 1.4b. When resolving vectors, this emphasizes that the Vectors are acting at the same point. By expansion, you can see that cos theta equals v horizontal by v. Therefore, vh equals v cos theta. Similarly, vv equals v sin theta. Worked example. A box of 20 Newton lies at rest on its slope, which is at 30 degrees to the horizontal. Calculate the frictional force on the box up the slope. Answer. Resolve the weight 20 newtons to the components parallel to and perpendicular to the slope. The frictional force F equals to the component of the weight down the slope. F equals 20 sine 30 equals 10 Newton. Now, test yourself. 11. Two forces of one magnitude, 1200, and the other of 1000, are applied to an object. The angle between the forces is 40 newtons. Draw a vector diagram and determine the magnitude of the resultant force and the angle it makes with the 1200 Newton force. 12. A rope is pulled so that it makes an angle of 20 degrees with the vertical. The tension with the rope is 500 newtons. Resolve the tension of the force into vertical and horizontal components. Revision activity. Work with a partner. One gives a key term from this chapter, and the other gives an explanation of the term. Change the roles until all the key terms have been covered. Do this at the end of every chapter. In this chapter, you have learned that all physical quantities consist of a numerical magnitude and a unit. To recall the SI-based quantities and their SI units: mass, kilograms; length, meter; time, second; current, ampere; and temperature, Kelvin. To express derived units as products or quotients of their base units. To use named units listed in the syllabus as appropriate. To use SI units to check the homogeneity of physical equations. To understand and use standard form. To recall and use prefixes and their symbols to indicate decimal, submultiples, and multiples of base and derived units: pico, nano, micro, milli, centi, deci, kilo, mega, giga, tera. To make reasonable estimates of physical quantities included in the syllabus. To understand and explain the effects of systematic errors, including zero errors and random errors in the measurement. To understand the distinction between precision and accuracy. To assess the uncertainty in a derived quantity by simple addition of absolute or percentage uncertainties. To understand the difference between vector and scalar quantities. To give examples of scalars and vectors. To construct vector diagrams and determine unknown vectors from diagrams. To understand that coplanar vectors are a set of vectors in which all the vectors lie in the same plane. To add and subtract coplanar vectors. To represent a vector as two perpendicular components. Thank you for watching this video. The upcoming video is going to be about kinematics.